Okay, welcome to lecture 14 of Submodular Functions Optimization and Applications to Machine Learning. Oops, and let's see. Okay, we're good. We're good. Thanks to the portable Wi-Fi hotspot, we're still good. Today, I think that everyone should have started hopefully reading this tutorial. This is Tom McCormick's tutorial. I think he doesn't use a notation that's very similar to ours, but at the same time, it's sort of a single source collection of all of the material that's relevant to what we're doing. But I think what we're doing is a lot of the concepts and the constructs that he's talking about in this paper, we're defining it and we're motivating it by our intuition that we've developed in terms of matroids. Because without actually having that basis, that matroidal basis, I think talking about dep and sat and sup and all of these things that we're talking about, exchange capacity, which we're going to define today, make very little sense. And so hopefully today's lecture will be a sort of an intuition booster. It's kind of like when you go to a smoothie shop and you can get protein booster or energy booster. This is intuition booster. That's what today's lecture is all about. And we only have two theorems to prove, but one of them I think we're not even going to prove because I want to try to see if it's possible to get through all 57 slides. And we have 57 slides to get through, at least that's our goal. Let's see if we can do it. But as we always do, let's do a review. So this is important, and this is important. Raise your hands if you have any questions on these two constructs. The set of tight sets and the maximal tight set. Okay. Raise your hands if you have any questions about the fundamental circuit of a matroid. Okay. This was a theorem that we talked about last time, which was the matroid partition problem. And this is essentially saying that you can take a set S and you can partition it into K independent sets where it's independent with respect to a particular matroid. And that's true. In other words, this is partitionable in this way such that it's independent in each respective matroid if and only if it's the case that for all subsets A, inequality 13.1 is true. And in particular, this turns out to be a submodular function minimization problem where if it's only one matroid, basically we're asking whether the vector 1 over k1, basically the vector that has all entries 1 over k is a member of the matroid polytope. And so that's basically a submodular function minimization problem in general. And in particular, it's a submodular function minimization because sums of matroid rank functions are submodular. And then the other thing that we mentioned last time was sort of in some sense, a closure of, but it's not really a closure. It's more like an additional fact about polymatroids that make it seem to us that it's very natural for them to be seen as a generalization of matroids. Namely, that the greedy algorithm has an optimality property associated with the polymatroids in the same sense as the greedy algorithm has an optimality guarantee associated with matroids. And moreover, the greedy is a defining property of polymatroids in the same sense as greedy is a defining property of matroids. So that's what this is saying here. We have these nice pictures. Anyone have a question about this picture? Yep.
Actually, I have a previous.
Yep.
Can you expand the term optimum? Expand on the term optimum.
Optimum. So we proved this last time. So what we mean by optimum is that there's no other vector x. Remember, this is the optimization problem, right? It's the linear programming problem with an exponential number of constraints, right? It has a solution. It's a convex programming problem. It's a linear objective with a convex constraint set. It's a set of intersection of half spaces. Optimum means that it's the highest solution. It's the maximum solution.
So
okay.
You're talking about W optimum. It's the best possible solution.
We're optimizing over x, right? So W is given, and we're optimizing over x. And what we're saying is that the greedy algorithm is optimal for all W. So W is a parameter to the problem. And we're then trying to solve the x that maximizes this problem for all possible W that possibly could be given. And we're saying that greedy gives us a resulting x, right? Greedy gives us an x. Greedy is the thing that we need to sort the elements according to W. And then we define the x based on the differences of the f's. And that is a first of all, a member of the polytope, if it's a submodular polytope, and then secondly, we saw by duality that it's optimum. We use convex duality. That's what we mean by optimum. And by being inside of the polytope means, like in this case, it's 3D, means we have to be inside of this polytope. This is a 3D polytope. And we've designated a particular face of this polytope, namely the base, as being important. Right? The base, we're going to get, so at the end of today's lecture, we're going to get some intuition about the base. In particular, we're going to notice that the base seems to be touching all faces. Like, for example, take the base here. Let me outline the base in case it's not clear. That the base is touching this face, this face, this face, this face, this face, and that face. Right? It's touching all of the faces that are defined by the constraints, right, of the submodular function. You know, not the positive ortho constraints, but the constraints that are defined by f of a, x of a is less than or equal to f of a. Is that a coincidence for this particular case? Do you think? No. It turns out that it's a necessary requirement, and we'll prove that. Or we will look at the proof of that. And we saw also that and extreme points are generated by the greedy algorithm. So if you're an extreme point, you have to be generated by greedy, by some ordering. And if you're generated by greedy in terms of some ordering, you're extreme. And we get that by Gaussian elimination. And this theorem is also something that's important. We define the sup function, the support of a set, and the sat function, which is the maximal tight set. And basically, we're saying that x is an extreme point. If you've got an extreme point of PF and B is between the sup and sat, then x is generated by using greedy order according to B. And we'll see some examples of this. We haven't proven this theorem yet, but we need more tools to prove this. Okay. And today's sort of a tool lecture. Any question on the statement of this theorem? So SAT, we're going to look at SAT again today and get more intuition about it. This is essentially the polymatroidal polytope where the edges are labeled by their lengths. And this is an important one for intuition again, because you can see if you zoom in on any one, you can see that each of these lengths are labeled by the conditional function. Right? And notice that, for example, again, if this isn't clear, that f of E1 given E2, E3 is less than or equal to f of E1 given E2 by submodularity. So therefore this length up here has got to be shorter than this length down here. Right? And so on and so forth for all these lengths. So I think this is a very good picture to get a strong intuition about what these polytopes look like and why they have that flavor. And again, notice that here's the base, and it's touching each of these faces. Okay. So here's another one that says that another important theorem that says that the minimizers of the submodular function form a lattice. They're closed under union and intersection. So we'll use that a little bit. And then we saw that the sat function, so the sat function is defined in this way, and we had this strange expression for the sat function. And so what we're going to do is we're going to show that 13.9 and 13.10 are the same. Okay. So 13.9 is essentially the union of the set of tight sets. Now, the whole notion of a lattice and taking the union of all elements is kind of like taking the join of all elements. When you're a lattice, you're guaranteed that all pairs of elements have a join, and so you can join anything together. And then if it's a lattice, then there's some sort of fundamental one element, which is like this element up here, which is the one. And if you union all elements together in the lattice, this is guaranteed to be unique. Okay. And then similarly, if you intersect all elements in the lattice, you get like the zero element of the lattice. And that's also guaranteed to be unique because it's closed under union and intersection. Right. Now there are lots of different kinds of lattices, and there's a whole bunch of stuff on lattices. And I could give a lecture on lattices if you want, and submodularity, but I'm not sure we're going to have time. But I could make some slides available. But for right now, I think it should be clear to everybody that if you're closed under union and intersection, that when you union everything together, we're going to get a unique 1 element, and if you intersect everything together, we're going to get a unique 0 element. And so what SAT is, it's the union of the tight elements, right? And the tight elements are closed under union and intersection. And the other thing to remember is that the tight elements correspond to this minimization of the submodular function f of a minus x of a, right, which is equal to 0. So you find the minimum, and the tight elements are those for which x of a minus f of a is equal to 0. And if x is the tight set, then we're guaranteed that there is some a such that f of a minus x of a is equal to 0. So we're guaranteed such that there is a minimizer. There is a minimizer of that submodular function f of a minus x of a, which is equal to 0. And if there's an extremal point, we know that there has to be such as well, because it's generated by the greedy algorithm, and we know according to the greedy algorithm that we're tight on all of the chains according to the greedy algorithm. Okay, that's what we talked about last time. Okay, so that's a review. Any questions?
I have a question.
Yep.
It's more like a basic question. We have 2 points, x1 and x2, and we have lattices corresponding to x1 and x2. So the unions for all the elements in the lattice for x1 will be different from all the elements of the lattice for x2. That is what we mean by union.
Now we're talking about union of sets, an intersection of sets.
Yes, so union of all the sets which correspond to x1 as the
there is no x1 and x2. So basically you've got an x, which is a vector, which is in the polytope. Right? It might be an extreme point. We're saying, let's say it is an extreme point. If it's an extreme point, then there's something that for which it's tight, right? And then we're basically saying a tight set is basically all sets such that x of a is equal to f of a. And if there are 2 sets that are tight, say A and B, then the union of those sets have to be tight, and the intersection of those sets have to be tight. And that's a consequence of submodularity.
Yeah, I get it. So what I'm saying is, if we have, say, fa is equal to xa and x1a, and fa is equal to
Okay. Okay, so let's look about this in the matroid case. And so the SAT function, we're going to see it as a polymatroidal closure function. So in the matroid case, basically, let's choose an independent set and then choose this vector. Okay, according to which is the incidence vector of an independent set, and then the set of tight sets are basically all A such that 1 I of A is equal to R of A, which R is the matroid rank function. So it's a matroid polytope in this particular case. So what is SAT in this particular case? So right, SAT is a valid submodular function, so we should be able to look at what SAT is in the matroidal polytope case. And that's basically just, here's the definition that we saw, right? It's the union of all tight sets, right? Then just using the definition, it's the union of all tight sets here. That's just, so tight basically means this. And equivalently, 1 sub I of A is equal to the intersection of I of A. You're just counting. Since the vector is all 1s, when you evaluate this here, you're just counting A intersecting with I, so that's just equal to this, right? It's just a counting thing. And now we definitely have that the intersection of I and A is less than or equal to I, right? That's just properties of intersection. Now, let's say that if you take some A here, which is strictly greater than I, and I is an independent set, and let's suppose that A doesn't increase the rank. So in other words, A is equal to, the rank of A is equal to rank of I. Okay, so now if we take an A that this is true, right? So in other words, the rank of A is equal to the rank of the intersection of I and A, which, because it's an independent set, must be equal to the rank of I intersect A, then that basically means that A has to be in I's span, right? So why is it the case? Because the rank of A is equal to the rank of the intersection of I and A, but the intersection of I and A is a subset of A, so now we've got an independent set, which is a subset of A, right? Because, in other words, we can say that I intersect A is a subset of A, right? We've got an independent, and this set is independent. We've got an independent set which is a subset of A whose span is the same as A, and so therefore A is I's span. right? In fact, A is even in stronger in A intersect I's span. So if A is in A intersect I's span, it's definitely in I's span. Okay, so that basically starts making SAT in equation 13.4 seem a lot like closure, right? Because the closure function in a matroid is basically all of the things that are in the span of the set that we're taking the closure of. So let's formalize this intuition. You could think of this as a proof. This might be obvious. But let's formalize it a little bit by saying that when we have a matroid, then for any independent set, we have that the SAT function is equal to the span function. Remember, the span is the closure function. Okay? So how do we do this? So we take an independent set. So we know that this is true, right? Just by definition. So the rank of I is equal to the size of I, which is equal to the one vector evaluated on I. So therefore, that means that I is a tight set, right? Because what does it mean for I to be tight? A vector to be tight means that, a set to be tight. Sorry, let me write it this way. So this means that I is tight for 1 sub I, since 1 sub I of I is equal to R of I. Right? So it's a kind of funny, weird tightness, but 1 sub I is a perfectly valid vector. This is a perfectly valid vector, just like X is a valid vector. And in order to be tight, we need to say X of A is equal to F of A. In this particular case, F is equal to R, and the vector is 1 sub I, and so 1 sub I of I is equal to R of I, means that I is tight for 1 sub I. And so that basically means that I is a member of the set of tight sets of 1 of I. And moreover, that since SAT is the biggest one, that means that I must be a subset of SAT, because SAT is the union of all such sets that are tight for 1 of I. Okay. Now we also know that I is a subset of span of I, right? Any set is a subset of its own span, right? So far what we've got is we've got I is a subset of SAT of I, SAT of 1 I, and I is a subset of span of I. Remember, what we're trying to do is show that these things are identical. Now consider some B in the span of I that's not I. Okay? Then we have that this is still a tight set. Now the reason why it's a tight set is because when we look at this quantity here, if we add B to I, since it's the 1 sub I vector, the element B has got value 0, and so when we count up that element, it's still going to be 0. So it's still going to be the size of I. But because we chose B in the span, that's equal to the rank, which is equal to I. So this whole equation, we're going to see this thing probably like 10 times in today's lecture in different form. Where we add something, it's equal to the size, which is equal to the rank of the bigger size, which is equal to the rank of the smaller size. So that green thing will pop up probably very redundantly and unnecessarily redundantly. Maybe necessarily redundantly, but I'm not sure. Either necessarily or unnecessarily, or both, or neither. But one of those 4 options, this wing will pop up at. Okay? Whatever that means. Which it doesn't mean anything. So therefore, what this means is that we've chosen a B in the span except for I, so that means that B is in the SAT, right? Because of the definition. So B is also a member of some tight set, so B has to be in the SAT. And so that means, therefore, what we've shown is that the SAT, that the span is the subset of the SAT. Okay? So now what we have to do is show the opposite inequality, the opposite set inequality. Remember to show that this is true. That's what we're trying to do. To show the opposite inequality, we take a B that's in the SAT, not in I, right? And now let's choose any tight set that contains B. That contains B. Okay. So first of all, it should be clear that B is in A. But it's not in I, because we're choosing B that's not in I, right? So B is in the SAT, not in I. And then we're choosing an A that contains B. So B is in A, but it's not in I. Secondly, why does such an A exist? Why? Well, because B is in the SAT, right? So B is a member. It's not an I, but B is a member of the set of tight set, is the maximal tight set. So there has to have been some set that when union together to get the SAT contains B. So we can choose some A, any A that contains B, which is guaranteed to exist by the definition of SAT. Now, if we look at the one vector of A, that's equal to this, which is equal to the rank of A. Okay? Now, why is that? Why? Because A is a tight set, right? So we're using the tightness in order to give us rank. Right? So we're choosing A in the set of tight sets. And so this is just the definition of tightness, but it just immediately gives us the rank of the set. So tightness gives us the rank or the valuation. Okay. On the other hand, we have that the rank of A is equal to this, but is also less than or equal to I, which is the independent set, which is the rank of I, right? So what we then have, putting these things together, is that therefore, since the rank of A is equal to the intersection, the rank of that is equal to the rank of is equal to that. Okay, so the rank of the intersection is equal to the size of the intersection. Why we have that is because any subset of an independent set is independent. So therefore, what we have is that the rank of A is equal to the size of the intersection, right? The rank of the intersection is equal to the size of the intersection. So that means that the rank of the intersection is equal to the rank of A, which is equal to the rank of the intersection union the residual, the stuff that's not in the intersection, which is A except for I, right? So we've got this bit here, and this bit here, and the red stuff is the residual. But that means that residual, the red stuff, must be in the span of the intersection. Because anytime we include this stuff here, it doesn't increase the rank. So that basically is the definition of span. That's in the span. And then the span of a subset is always less than or equal to the span of a superset. So therefore, A except for I is in the span of I. But since B, remember we took B in A, not in I, that means that B is in the span of I. So we started taking B in the SAT, except for I, and we've got that B is in the span of I. And so therefore SAT is a subset of span. In other words, SAT is equal to span. Now, this is just for the matroid case. So in the matroid case, you can think of SAT. Now, the other thing to remember again, of course, is that here, we have an extreme point, right? And why is it an extreme point? Because we're taking the characteristic vector of an independent set of the matroid, which is an extreme point of the matroid. There's a lot of ways of seeing it. One, you're taking the convex hull of the independent characteristic vectors of the independent sets of a matroid. Two, you can get any of these independent points by taking a greedy order that increases the rank. So these things generally will be used when the vectors that we're talking about are extreme, meaning they're not convex combinations of distinct other points inside of the polytope. I mean, you could sort of define them for other points inside of the polytope, as we will be, but they're really useful for when you get to the extreme points, because it turns out that the extreme points of the polytope really are going to be those things that correspond to important combinatorial properties of the underlying submodular function. Now, one of the things you might ask is, well, span is defined for any C, right? But if we take the incidence vector of any C, is that going to be in the matroid polytope? So, here's a matroid polytope, right, which is a triangle. And here's the incidence vector of let's say this is E1 and this is E2. And this vector is the incidence vector of 1 of E1. This is the incidence vector of 1 of E2. But now if we take C, which is, say, if C is equal to E1 and E2, then this guy is equal to 1 of C. So that obviously is not a member of this matroid polytope here, right? So the question is, in SAT, now in the span case, if we want to say that SAT is equal to the span, it might, like, so this is saying it might not even be a vertex or even a member. It could be completely out. So span operates on more than just independent sets, because we can take the span of C in any matroid, and that's perfectly sensible, right? The span of C is anything that, when we add it to C, doesn't increase the rank, and span doesn't need to be independent. So what you could do is you could sort of fix this up by saying, well, the span of C is always just defined to be equal to the span of B, where B is a base of C, and you take any base of C. And so therefore we could define SAT in exactly the analogous way. We could say that SAT of 1C is equal to SAT of 1B, where B is any base of C. Or more generally, you can imagine defining SAT to be the SAT of any P basis. Remember the notion of a P basis, the maximally independent subvector of a given vector? We could take any P basis of Y, which we know has the same component sum because it's a polymatroid. We could take any P basis of Y and say the SAT of Y is equal to the SAT of the P basis of Y. Right? Now what if you're an extreme point? If you're extreme point, that means that you're your own P basis. Right? If you're extreme point on the polytope, you can't move. If you try, you're not a convex combination of any of the other vertices of any of other points in the polytope, and so therefore you're maximal with respect to the polytope. Or if you're not maximal with respect to the polytope, then any P basis of U has got to be a subvector. So therefore, when you're an extreme point, you are your own P basis. Right, so let me just write that down. That's something worth mentioning. Okay, so here's an exercise problem for you. What if we were to define SAT more generally in this fashion? So this is basically allowing C to be not independent vectors. Oh, sorry, C to be not independent sets. So is this still true? So that's an exercise for you to prove. Okay. Now SAT is therefore for a matroid exactly the span in the matroid. Okay, so we have this. This is basically what we've proven or shown. And then now moving to the more general polymatroidal case, we have that SAT is the maximal minimizer of this submodular function, which is not necessarily monotone. And then, so therefore span, you can think of the span function as the maximum minimizer of this submodular function, which is the difference between a rank function and an incidence vector. Okay, which is kind of interesting. It's basically saying that if you happen to want to solve a span problem in a matroid, and you had a generic submodular function minimization toolkit, it would be a little bit of overkill, but you could solve span queries in matroids with submodular function minimization. So I know that, for example, like this morning when you were eating breakfast, you were saying, God, I wanted to solve this span problem in matroids, which actually, to be honest, it's a very important problem and useful in machine learning. And if you're interested in why it's useful, come ask me. But the submodular function minimization can solve span queries. Okay, now SAT is useful in that it can be seen as we saw before, as some sense it has a tightness quality. It's tight in terms of being a member of the polymatroidal element. So we said that SAT can be defined in this fashion right here. So let's just look at this a little bit, just to make sure we understand. Okay. So what we're saying is that SAT is equal to all elements E, such that, so think of E as like a direction. So remember, E is like the index of a direction in this n-dimensional space. Right, so basically, SAT is basically defined in this equation as saying all directions, right, all E, such that if you move epsilon in the positive E direction, you leave the polytope. So if this is a little polytope here, it's saying that we cannot move in this direction and we cannot move in this direction, right? Those are the two directions. So basically SAT in that case corresponds to E1, E2. And this is X right there. So how is it then that that's equal to this maximal tight set? So let's see if we can formally show that. So we've got SAT, which is just equal to the definition that we just saw, right? Now this is just another way of stating it. It's basically saying it's all directions E such that for all alpha that's strictly greater than 0, if you move in the positive E direction, you leave the polytope, but that's basically saying that there exists some violated inequality. It's basically there exists some A. Remember, A is a set and sort of indexes the inequality. There exists some A for which the inequality is violated. And violation basically means that we have strictness in this particular case. Right? It's greater than, or outside of the polytope. There might be more than 1, but there can't be less than 1. That's what violation means. So another way of saying that is to add the quality that we need to include E inside of A. And the reason why we need to include E inside of A is because if E was not in A in here, then that index would just be, that increase according to alpha would just be 0. Because it's basically like alpha times 1E of A, but if A doesn't contain E, then the E direction is not in A, and so we're not summing up that additional increase. So we have to, it only makes sense to include E in A. Right, so I just said that. So then when we look at what is alpha times 1EA, alpha times 1EA, that's just equal to alpha, right? Because basically 1E is just characteristic vector of E, and we're saying that that for E is in A, that's equal to alpha. So then we just sort of replace that whole expression with alpha there. So then now we can write this in this fashion. If taking a look at this expression 13.13, it's basically saying it's the directions E such that for any epsilon, any alpha greater than 0, x of A is strictly great, plus alpha is strictly greater than f of A, right? So so no matter how small alpha is, if we add any non-zero value to x of A, we're greater than f of A. So what is the only possible value of x of A that has that property? F of A, right? So that basically says that we can essentially get rid of the alpha and just say, well, x of A, the only possible value of x of A that has this property up here must be f of A. So x of A has to equal f of A. Okay? But notice, interestingly enough, we've now sort of gotten rid of alpha entirely from there. So we say it's all directions E such that there exists an A that contains E such that x of A is equal to f of A. Right? Remember where we're going. We started with this up here, right? So, but this is basically saying any E such that there exists an A containing E such as x of A is equal to f of A. That's basically saying, well, any A that's tight is such that there's an E that contains it that's tight, right? That's kind of a silly, almost a tautology. It's sort of a 13.15. But basically now it's saying any tight set A, so any set A that has the tightness criterion, then for any E containing A, we have E being a member of SAT. So therefore SAT is a superset of any such tight A. So any tight A, SAT has to be a superset of it. But there's nothing else that can be in it, so then basically SAT is equal to the union of all of these tight sets. So that, therefore, it's the same definition. Oh, sorry, there's one other thing. So we need to say that SAT's a subset of it as well. So if we have any E in SAT, then E is itself a member of a tight set, which means that there exists some A such that it's tight. So any member of SAT according to the tightness definition must be such that just by definition of SAT, there's this 13.15, and so therefore we've got the other inequality here, and so therefore the two definitions of SAT are identical. Okay, any questions? So you can sort of geometrically think about the generalization of closure in a polymatroid via restricted movement of points inside of the polymatroid. And for those people who are interested in polyhedral combinatorics, this is a really, really great thing. If you like shapes and geometry, then this is nice. And especially when you're trying to reason about very complicated algorithms like submodular function minimization. Now, saturation capacity is another fundamental concept there's a tool that we need. And it's also a generalization of a matroidal property, interestingly enough. So let's consider the following. So we've got some point x in the polytope, and we're taking a particular direction E. And this is, consider defining this quantity, which is the largest possible alpha, such that if we move in the E direction by alpha, we still are inside of the polytope. So in other words, if we move anything more than this value, we leave the polytope. So this is identical then to saying that it's the maximum alpha such that we satisfy the inequality, the sort of polyhedral half-space inequality restriction definition for any such A that contains E. Because obviously any A that doesn't contain E doesn't matter, because that direction doesn't matter since it's not included in A. In other words, I think I have that written down. That's basically this. So then, again, using that this part here is just equal to alpha, which is this, we've got this expression down there. If you have any questions about this, then let me know. This is getting a little, maybe it's a little bit tricky. But now if we just rearrange this thing here, this is the maximum alpha such that alpha is less than this difference. This is now starting to look a little bit like submodular function minimization. Maximum alpha such that alpha is less than this difference for all A that contains E. But the maximum alpha that's less than that for all A is basically equal to the minimum of f of A minus x of A over all A that contains E. And so therefore, that alpha is equal to this submodular function minimization problem. It's a restriction of submodular function minimization that contains E. But remember, that's still a submodular function. If you take a submodular function, we said this in lecture 2 or 3 maybe, that if you take a submodular function and you forcibly include a ground element, and then consider a new ground set which consists of everything but that ground element, and you're taking subsets of everything but that ground element, but where the valuations always include that ground element in the original submodular function, you're still submodular. So this is therefore a submodular function minimization problem, again. And this is called the saturation capacity. Fujishige notates it with C x v. Okay, so here's its definition. We proved both. All right, we proved both of these guys. So, you can relate this to SAT, and if you take any non-saturated element, for example, like we take an element that's not saturated, the complement of SAT, then we've got a strictly positive saturation capacity, right? On the other hand, if we take a saturated element, then the exchange capacity is equal to 0. So you could sort of define the SAT by saying those elements with exchange capacity 0. This is all relative to a particular x. And the other thing maybe to note is that if we take any alpha between 0 and exchange capacity, then we're safe to move in that direction. So if we were to draw a picture, say, with a polytope, then the exchange capacity of this thing would probably be, like if we took this point here, we could move in this direction up to C. Let's say this is X, and this is E1, and this is E2, and this is C hat of X, E2. And this would be the height of this thing, how much we could move in that direction. Okay. Now, another fundamental function is called the dependence function, the depth function. And this really sort of gets into the nature of what, in my case, the epiphany I had, which was not much of an epiphany, I think, but what made me realize that submodularity is really just a generalization of things like entropy and is really sort of a natural information function is really this dependence function, because it sort of measures the way that things depend on each other, elements depend on each other. And we're going to sort of look at this a little bit in the context of how people have looked at entropy in information theory, but how this naturally generalizes and how certain polyhedral shapes correspond to certain dependency-like structures that you might find in information theory or even in a graphical model like in a Bayesian network. So we'll see that next. I think we won't actually see that until we get to these examples over here. These examples over here, that is. But this is where we're heading. I think this is really cool. So, but please try to pay attention, because this may seem trivial and not important, but it actually is. It's a very, very deep intuition, which if you get, you will develop a really nice intuition of this stuff. So we're going to define something called the depth function, or the dependence function. First of all, let's define the E containing tight sets. So D, remember D of X, those are the set of sets that are tight at X, right? Raise your hand if you remember what D is. Okay. Now, dx of E is basically is the subset that contains E. Right? Now that's going to be a lattice too, right? Because obviously if you're in D of XE, that means that you contain E. And if you're two sets that are in D of XE, you also contain E. So the union of those two sets are going to contain E, and the intersection of those two sets are going to contain E. So therefore D of XE is also a lattice. It's a sublattice. So you can write it, like if you think of this as a lattice, the sublattice, sometimes is like seen as a little triangle inside of a little diamond inside of a big diamond. Yeah. So like let's say that the lattice is a 14-carat diamond and the little lattice is like a 7-carat diamond. I don't know. What does carats mean? Why do we measure diamonds in vegetable units? I don't know. I have to put a little bit of nonsense into this lecture. No lecture is good without a little bit of nonsense. Right? So we've had our daily fill of both carrots and nonsense, and now let's try to sort of define the depth function and get some intuition about it. So the depth function is basically equal to the minimal element in the lattice of E containing tight sets. And since it's a lattice, it's unique. It's the unique minimal element of the E containing tight sets. So remember, dx of E is the E containing tight sets, and dep of x of E is where we take the minimal of such element. And it's only valid if we take E inside of sat, right? So it's only for the saturated elements, right? It's defined to be the empty set if E is not in the sat. Okay. Why is that? Because, obviously if E is not sat is all of the elements that are tight, right? And if E is not in sat, then how can you be an E containing tight set? It means that you're not tight at E, so you can't be at the tight set. That's called dep, or dependence. So there's a minimal X containing tight set. And it exists because it's a lattice. Now, here's essentially a picture that sort of represents the lattices. So Now, if you look at Fujishige's book, one of the reasons why it's challenging to read is because he, from the very, very start, talks about submodular functions with respect to general lattices, which need not be 2 to the e, which is basically all subsets of a given set. But you can take any sublattice of that. And lattice properties basically are, you need to have essentially a set of elements, and you need to, so every pair has a unique join and a unique meet. Okay, and any sort of algebraic structure which is a lattice is something for which a submodular function could be defined on. In fact, if you go to the very, very early picture, let's go to page 1 even. Let's go to page 1. So this, oh no, we don't have it here. I take it back. If you go to the video and the musical introduction, and you see this thing that floats up for some reason, which is in this ridiculous music and this ridiculous floating structures in the intro to this class, which you don't get to hear unless you watch YouTube. Well, that thing is a lattice, right? That's actually a submodular lattice. And that's something for which join and meet is uniquely defined. Now here, we're basically saying we're not really sort of worrying about that. We're not talking about submodular functions defined on a sublattice of 2 to the e. The 2 to the e is called a Boolean lattice. It's a binary. It's a distributed complemented lattice, which is isomorphic to 2 to the e. So here we're talking, but let's not worry about that because I think that adds complexity. By the way, something else someone once asked was, is there an equivalent to convex sets? Like in a convex function minimization, we say we minimize the convex function subject to a convex set, right? So we say, well, what about discrete optimization? We can minimize the submodular function subject to a convex constraint. Is there any analogy to a convex constraint? Turns out a sublattice is the analogy, because it turns out you can minimize submodular functions subject to sublattice restrictions in polynomial time for many kinds of sublattices. Any distributed any Boolean distributed lattices you can. But here what we're talking about, let's just start from the ground set. So this big green diamond is the ground set. It's 2 to the ground set. So it's all subsets of E. Now this inner diamond here, this one, let's make it a little bit thicker. This one here. We choose a particular x. And that diamond is basically the lattice of x-tight sets, right? So any member in there is an x-tight set. And then the sublattice, let's say it's this one here. That's the sublattice of x-tight sets containing E. Okay. So the constructs that we're defining here and that exist in Fujishige's book are sat and dep. Okay? But we're, in addition, defining non-Fujishigian constructs, which are sat xe and dep of x. So he doesn't actually define that. But, I mean, it's very natural to define them. I was using the term dry, because it's kind of like, if sat is saturated, then dry is dry. But that's a really dumb term. In fact, I was planning to remove that term from the lecture slides today, but I don't know. Bear with me. These are evolving slides. But let's just pretend, for maybe humorous reasons, let's call it sometimes dry. But what is true is that the two blue things that I highlighted are the things that we just defined. So sat in the matroid case is a closure, is the span or the closure function of the matroid. What is dep xe? Well, first of all, dep xe is basically the minimal element of the E-containing tight set. Sat xe is the maximal element of the E-containing E-containing tight sets. And dep of x, or dry, is the minimal x-tight set. So this is all, I should maybe add, this is all for some x in P of f. Right? So this is all relative to some particular x. If we change x, we get a completely different set of items, right? Although everything would still be a sublattice of the big diamond. We would just move this first sublattice around somewhere in there. Yep. Question?
When you say minimal element, you just mean the intersection of the sets that satisfy that?
That's right. It's the minimal element. So, basically, if you're defining a lattice based like in the following way. Or you're saying, okay, you take any two distinct elements and the meet, and there's a distinct meet and a distinct join. So if you take any two distinct elements, so every element joined with itself is itself. Every element meet with itself is itself. So if you take any two distinct elements, then it's join. It's got a unique join and a unique meet. And so therefore we just keep doing this over and over and over again. And we're going to get a unique single element at the bottom and a unique single element at the top. That's guaranteed by the lattice property. Because it's a lattice. Yeah.
What is the significance of this diamond shape? Is it something similar to what we have for the polymatroid shapes?
Yeah, I should have... let me just give you an example. I have a... I'll give you a very, very little lattice. Just for right now. Just let's see if we can do this. So let's start with, let's say that, I'm just going to make this up. I hope I don't make too many mistakes in doing this. So let's say that E is equal to the elements E1, E2, E3. Okay, so it's a 3-element ground set. So let's first of all start with a lattice where we have this one these are lattice elements now. So the lattice element at top is equal to E1, E2, and E3. Okay. And at the bottom, we've got a lattice element. I should have had a picture for this, which is the empty set. Okay, so the empty set at the bottom, ground set at the top. Now let's define 3 elements in the middle. So let's label this element as E1, this element as E2, and this element as E3. Okay? And the meet of any two of those elements is the empty set, right? Because the intersection of E1 and E2 is equal to the empty set. So now what we've done is we've defined 3 sort of ground elements, and this by says why it's called ground elements, because it's like the empty set is like the underground element. The first layer of the lattice is like the ground elements. This is our ground set. But now what we're going to do is we need to have a join for each one of these. So let's say that this one here is the join of E1, E2. This one here is the join. Now, would it be correct to do that? No, because every two lattice elements has to have a unique join and a unique meet. So this would not be a lattice. This suddenly would lose the lattice property because E1 and E2 has two joins. That's not valid. But what is valid is to do this, because we haven't yet given a join for E1 and E3, and let's just name this guy E1, E3. And then this guy here, there's one last guy we haven't done, E2 and E3. So this second layer of elements is not the ground element anymore, but it's pairs of elements. And then lastly, if we union together any two of the yellow layer, we get this, right? So E1, E2, so unioning together E1, E2 and E1, E3 gives us E1, E2, E3, which is the V element. Similarly, if we union together these two, we get this, right? So any pair. Now, no one has said that a particular element in the lattice can't be the join of multiple pairs of other elements. So, like for example, we have this ground. Let's just label this green. We have this ground guy, E1, E2, E3, which is the join of 3 pairs of elements. Namely, let's do this in color. So if we union this guy and this guy together, we get green. If we union together this one and this one, we get green. And if we union together, say this one and this one, we get green as well. Okay. But that's fine, right? As long as any pair, like the magenta pair or the red pair or the blue pair gives us the same element, that's fine. Now notice that this is a diamond-like shape, right? Now, what does a sublattice mean? Well, what if I were to say carve out this particular sublattice? So that's the E containing sublattice. Sorry, it's the E1 containing sublattice, right? It's still a lattice, right? But now it's another diamond shape, except that the ground set is here, right? The zero element is kind of like this one. The ground set is here, and then the full set is up there. Right, so in any lattice, there's sort of one distinct guy. Now, because it's a property of a lattice, you take the intersection. In any of these lattices, you take the intersection of everybody, the union of everybody. If we take the union of everybody, we're going to get to the top, which is a point. It's unique. And if we take the intersection of everybody, we get the bottom. So now that means that because union and intersection are perfectly valid join and meet operators, that the set of minimizers of submodular functions forms a lattice. Okay? There's even a more powerful theorem that was recently proved that says that if you're a function whose minimizers form a lattice, you're submodular. It's amazing. So, in any event, that's what a lattice is. So now so does that make sense? Did I answer your question? Okay. Now, we don't have, I've got a bunch of, I could do a full lecture on lattices, by the way. Is anyone interested? Or should I just do a YouTube lecture on lattices? I don't know. We're running out of time. I think we're sort of behind. So what I could do is I could do an extra 2 lectures in finals week. Are you guys interested in that? You guys are all so excitedly awake for the current lecture. I'm sure that you would love to have 2 more 2-hour lectures from me. But I would be happy to do that if people are interested in it. You're all sort of jumping on the edge of your seats. Anyway, I won't. I'm sure the YouTube people are all. They would be happy. Anyway, so dep and sat in a lattice. So let's say we've got some x, and we've got a distributed lattice of tight set. So now we know that it's a lattice, right? And we know what a lattice is. And so sat is like the one element of this lattice, right? It's like that top guy. And then the zero element is this dry guy. It's just the bottom one. So that's like the first sublattice of the big lattice of 2 to the e. And so we can think of dry, and this is really critical. Dry are like the elements that are necessary for tightness. If you are a set that does not contain any of the elements in dry, you're not tight. Why? Because the intersection of all tight sets have those elements. Now, it's not necessarily the case that this is not the empty set. Dry could be the empty set, which means that there is no elements that are necessary for tightness. But there are instances, as we will see when we look at some of the examples in 2 and 3D, that there are cases where dry is not the empty set, which basically says that if you don't contain this element, you're not a tight set. Okay, so it's like, I think of it like it's the necessary for tightness set. And so therefore we can define dry in this sort of interesting way, which says that dry is equal to all E prime, such that if you're a set that doesn't have E prime in it, you're not tight. Okay. And I just said that. So so therefore, maybe rather than calling it dry, which is sort of a silly name, maybe a better name might be N-tight or something, necessary for tightness. It sounds like a name of a soul band from the 1970s. N-tight. Have you heard N-tight? Right. They're great, in tight. Actually, no, you'd need an apostrophe
Yeah.
in tight. Then it would be a soul band from the 70s. Okay. Great. Does anybody know what a soul band from the 70s is? No, I don't know what that is either. You really don't know what a soul band from the 70s is? Have you heard, like, the band Confunction? Have you heard of that band? No. Has anyone heard of Confunction? No. Okay. We should do a music class, a 70s soul music class. Okay, so dry need not be the empty set. I think we're going to see an example. So, but what we want to do is we want to define the dep x of the E function set, because that's sort of the one that. So now we've got some x, and we've got some x in the polytope, and we've got some sat E in the sat. And then here's the set of E containing tight sets, right? dx of E. And so we can define a one element of this sublattice. So this is like this inner diamond that we saw in the big triangle. So we have the big triangle, the medium triangle, and the baby triangle. This is the small triangle. Sorry, the small diamond. And so this is sort of the one element in that small diamond. But similarly, we can define dry x of E, which is the minimal E-containing tight set. It's like the zero element of this sublattice. And those are the elements that are necessary for E-containing tightness when E is in sat. Okay. And another way of viewing it, again, in terms of this like necessity requirement, is saying that dry, which remember is equal to dep, right? Dry of xe is equal to dep of xe. That's basically saying it's all elements E prime such that, first of all, for all sets that don't contain E prime, but that do contain E, you're not tight. Right? So it's basically saying that you have to contain E, but you're not containing E prime. So it's the necessary elements for E containing tightness. That's the way of saying it.
If E belongs to all A, then the intersection will have E, right?
If E belongs to all A?
If E belongs to all A by definition, then its intersection will contain E. So dry X, E will have E.
No. So think of this is a definition, right? So it's all elements E prime, right? That's saying that if you're a set that contains E, but you don't contain E prime, you're not tight. Right? So it's saying that it's the necessary element. So E prime is necessary for tightness. If you're an E containing set, but you don't have E prime in it, you're definitely not tight. There are the E containing sets that are tight, and there are the E containing sets that are not tight. And what it's saying is that if you are an E containing set that is tight, you must have all of the elements in dry in you. You must be a superset or equal to dry. So that's basically what I just said. So, I mean, just these are the same equations. So dry is really equal to dep. I was just calling it dry. But it's really, Fujishige calls it dep, and everybody else calls it dep. So we should be calling it dep. Although some people call it d of x comma e. Like in McCormick, I believe he uses d of x comma e. Is that right? I think that, yeah, I know you read the paper. That's why I'm asking you. I think he uses that. Okay, so now, remember the fundamental circuit of a matroid? So we're not doing, let's see, are we going to reach slide 57 by the end? What do you think? How are we doing? No? It's impossible? I should stop talking about 70 soul bands. So E is so we've got a matroid now. Let's do what we did for sat. Remember what we did for sat? We looked at it in the matroid context and we said, oh, interesting, sat is just equal to the closure. What do you think dep is in the matroid case? Well, it's the fundamental circuit of a matroid, as you will see. So one thing to remember is that we have this. We know that this is true in the matroid. And let's choose some particular element that's in sat that's not independent. And let's take some E containing set A. okay, that is such that I intersect A spans A. So this is exactly what we did in the SAT case. So then, as we saw, that this I intersect A serves as a base for A. And any A is, not an independent set, and so there's a sort of a fundamental circuit that inside of that's added. And in fact, like if we can take some E that's in A, not in I, and since it's got the same rank, since the rank of A is equal to I intersect A, we can take any E inside of A but not in I, and we add it to this, and it increases. It does not increase the rank, and so it contains a circuit. It is the circuit. Now let's consider this case. Let's say that we take E in SAT, not in I, and consider what dep is. So it's dep of 1 sub I comma E. Right? So it's dep on the vector, which is the characteristic vector of the independent set of the matroid, then evaluated E, where E is chosen from SAT of that same vector 1 sub I, but not the independent elements itself. And what we're going to do is we're going to argue why this dep gives us the fundamental circuit of the matroid. Okay. So first of all, here's the definition of dep, right here. It's basically saying we're taking the intersection of all E containing tight sets, and the vector happens to be 1 sub I in this particular case. So it's E containing 1 sub I 1 sub I tight sets. Okay. Now we can just write this in a different fashion, just by noting that these two things are the same. And then we can write it as a submodular function sort of minimization problem, right? So we've got the submodular function, the rank of A minus this modular function I intersect A. So it's the intersection. So it's like the smallest minimizer of that submodular function, right? But by submodular function minimization, we know that the minimizers are a lattice, and because it's a lattice, we know that the smallest minimizer is unique, the minimal minimizer is unique, and it's E-containing. So there exists this unique minimal E-containing set A, which is dependent in this fashion, meaning that E is not in I, so basically it has to be the case that I intersect that A contains an element that's not in I. So that means, but that's basically saying that the rank of A is equal to the intersection of A and I. So that's equal to the rank. So this therefore means, because of the minimality, what's the only set that would have that property? It's a circuit in the matroid. The circuit would be the minimal set that when you add E to it, there's the dependence, right? And the dependence is guaranteed by this property, right? That the intersection is equal to the rank. The size of the intersection is equal to the rank. And if it wasn't a circuit, like suppose you had a circuit and you had one extra element, right? Well, the extra element is not in I, so it's not going to increase the intersection with I, right? And then it's another element, but it's not dependent, so it's not going to increase the rank, and so therefore it's not going to be minimal. So it's only the circuit that satisfies the minimality property, which is guaranteed to exist by the lattice of minimizers of the submodular function. So therefore, in the matroid case, dep is the same as the fundamental circuit. So remember before, we gave this very curious definition of what happens when when we ask for the fundamental circuit and E is in I. So like if E is a member of I and then we ask for what Ci comma E is, we just define it to be equal to E. So now we will discover why we did that, and the reason why is because dep is equal to that. So basically, if you look at the definition of dep from a couple of pages ago, here, what happens is that if E is a member of I, we keep taking intersections, and it basically E itself satisfies that inequality. So like the rank of element E is equal to 1 for element E, and that becomes the minimal element, and so the depth of 1 sub I comma E when E is in I is equal to E itself. So therefore we just define this to be this. And of course, the other thing to remember is that the depth function is basically a tight set. And so we're defining it in the more general polymatroidal case, and it's going to be a tight set because we've defined it in this other way. So just to summarize of sat and dep. So we've got sat, which is like the span or the closure in the matroidal case. It's the maximum saturated X-tight set with respect to a particular X. And we have a number of different definitions for it. It's like the closure of X or the sat of X. So there's a number of different ways. And what we did also is earlier we showed that it's equal to 13.36. For dep, like if we choose a particular E which is in the sat, then the fundamental circuit, or the dep, more generally the dep in the polymatroid case, is the minimum E containing saturated set. X-tight set. And we said it's equal to this. But now we have another equation that corresponds to the same thing, which is a movement restriction in the polymatroid polytope, 13.37. So we don't know is why is 13.37 true. So let's, what we're going to do is when we come back, we're going to see why 13.37 is true. And why there's a very nice geometric intuition in the polytope of the fundamental circuit of a matroid. Okay, so let's pause for a few minutes and come back. Okay, welcome back. So what are we going to do? Okay, so let's start on this. So we want to now sort of get an understanding of this expression down there. Let's just sort of look at what it is. So one thing, let's just take a look at it for a second. What this is saying is like it's all elements E prime. Let's just erase all of this stuff so we can talk about it. It's all elements E prime such that there exists an alpha, so that there just has to exist an alpha, which is a non-negative alpha. In fact, it has to be strictly greater than 0, such that starting at x, okay, so we're starting at x here. If we move in the positive E direction by alpha, and we simultaneously move in the negative E prime direction by the same amount alpha, we are still in the polytope. Okay? That's what basically this says. And this is for the particular E. So in some sense it's saying that we've got an X, and it's kind of like saying, well, if you move in the positive direction of E and simultaneously move in the negative direction by E prime, then you don't leave the polytope. Right. Now, if you're deeply embedded inside of the polytope, then it seems to me to be reasonable to assume that, okay, well, you could move any direction in the positive direction in one and the negative direction in the other, and you'd still be in the polytope. The underlying directions that you're moving are all going to be, thanks to essentially this thing, they're all going to be like 45 degrees, right? So, like, let's say that you're deeply within a polytope. Like, let's say that you're here. Okay. So if you move a certain amount this direction and you simultaneously move a certain amount that direction and you end up here, you're still going to be in the polytope. So if you're inside, it seems like there's always some alpha for which you could move a little bit this way, and as long as you move a little bit that way, the amount that you're moving is going to be in this negative 45 degree direction. Right. This becomes more interesting, however, when X is in sat, when X is really saturated. That's one of the tight sets. Then it becomes not so clear. So let's sort of like look at this. First of all, note that this is like an exchange property, right? This is kind of like saying you can do one thing if you do the opposite in the other thing. It's like I can exchange the E direction for the E prime direction. Right? So it becomes interesting when we're on an extreme point. So now look at this. So if back to the matroid case, if we take an element in E, which is in the span of I, but it's not I. So it's in the span of some independent set, but you're not taking the independent set. Then anytime you add E to I, you're no longer in the independent set. You've left the set of independence sets, right? Because you're spanned by I, but not I. Now if we take, I'm going to modify this a little bit. So if we take, this will make more sense a little later. But if you take any E in the sat except for the sup, right? So in other words, you're taking an element in the X tights from the maximal X tight sets, but not the ones for which you're positive, namely ones for which you're 0. And then basically what it's saying is that if you move in that direction, you leave the polytope. Okay? Because you're saturated in that direction, right? It turns out that even if you take elements that are in the sup as well, like if I didn't subtract off the support, it might not necessarily be the case that you leave the polytope, but you would no longer be a subvector of X, right? Because obviously you get bigger than X. But in this particular case, if you subtract off all of the X, if you subtract off all the positive ones and the only ones that are 0, if you do this thing, then you're going to leave the polytope. So you can see that there seems to be an analogy between span and the independent set and sat and the sup of an extremal point. Okay. So let's mark this, and this is a really important thing for this guy and this guy. Now, if we take a fundamental circuit, which is CIV, and we remove any element E prime from it, then we've recovered independence, right? So, therefore, you can think of CIV as all of the elements that when you remove it from that circuit, you can recover element. If you take any element from the fundamental circuit, if I've removed that element, I'm sort of free to add E to I. So in other words, an interesting way of looking at the fundamental circuit is as follows. It's basically saying that the fundamental circuit is equal to those elements A, such that if I add E to I and therefore create a dependence, but I remove A again from that, I recovered independence. So it's kind of like the fundamental circuit is like an exchange. It's like essentially a set of exchange elements. Like if you insist upon adding an element E to I, but you want to get back independence, then you remove the elements A. Now, this should hopefully jog your memory because we've seen this before. Does anyone remember where we've seen this? Remember in the matroid intersection problem? And remember when we were basically creating this border graph? And what we were doing is we had these two matroids and we added an element. As long as we're still independent with both matroids, we were fine. But as soon as we add an element that's independent but not independent in the other, what we do is we go to the other matroid, we look at the fundamental circuit, and we remove those elements. Or we consider removing one of those elements from the fundamental circuit, which is guaranteed in the other matroid to recover independence. It's guaranteed in the first matroid to recover independence, or to keep independence since we were independent in the same thing. But it gives us another option. So then now back in the first matroid, maybe we can add some other element that will be independent in both matroids. And we're guaranteed that if, the theorem said that we're guaranteed in the matroid intersection case to be able to go back and forth using these fundamental circuits properties. So we gain that intuition, and so this is exactly the same intuition. It's basically saying that the fundamental circuit are those elements that when you can remove, if you add an element to an independent set and you're no longer independent, it's those elements that you can remove and recover independence. Now dep, all right, let's see, I think I've already said this. All right, this is what I've just said. And it's underlined, so that means it's important. So the question is there an exchange property, a similar exchange property in a polymatroid that corresponds to vector movement? Right? Because remember, sat we corresponded to like a vector. It was essentially a set of directions for which you were restricted from movement while being in the polytope. Like what does it mean to have a vector movement restriction? Like it might be, for example, exactly like we saw that previous definition by saying that if you move positively in the e direction, maybe there's a corresponding other direction that you would have to also move at the same time and at the same rate while staying independent, namely staying inside of the polytope. So let's look at this intuition. So looking at it as dep is the set of negative directions we must move if we want to move in the positive e direction, starting at x and staying within p. So here's two examples. So let's look at the left example first. So the left example is all this stuff over here. So let's just look at that example. So first of all, this is a matroid. This is a possible matroidal polytope, where basically it's saying that A is independent of B, or A and B are separable, or A and B, A and B, you're modular between A and B. Okay, so there's no dependence. And so basically it's saying that if the vector is, say, here, that A intersect dep of E is equal to 0. Okay? So this is, again, using this intuition up here. It's the negative directions we must move if we want to move further in the E direction. So we want to move further in this E direction, right? This way. Can we move down? And does moving down help us move further in the right direction? No. Right? So basically dep, x comma e, and a have zero intersection, or empty set intersection. And notice also that in the matroid case, there's no dependence between e and any element in a. If this is a matroid, or even if this is a polymatroid, then whenever you have these squares, polytopes, that corresponds to sort of perfect independence. If it's a entropy function, it corresponds to the random variables being statistically independent. If it's a polymatroid, it corresponds to modularity between A and B. And remember what modularity between A and B would mean. It would mean, for example, that, if this isn't clear, it would mean that, for example, f of x is equal to f of x intersect A plus f of x intersect B. In other words, the interaction between A and B doesn't matter. Right? Now let's look in the second example. So does the first example make sense? Second example. This is a real polymatroid, right? Now, geometrically it's saying, well, okay, so we want to move in the E direction, which is to the right. And this guy is saying, oh, well, if you want to move to the E direction to the right. Now, remember, this might be some face of some larger high-dimensional polytope, but here we're just talking about two particular directions, where we're talking about sort of a separation between B and A. And it's saying that there is a dependence between B and A. And in particular, it's saying that if you want to move further in the E direction, you can do that if you're willing, if you're at this point, you're starting at this extremal point here, you can do that. You can move down. You can move to the right in the E direction as long as you move down in the A direction. And so we can then therefore make that path. And so in this particular case, A is a subset of dep x comma e. So in some sense, it's saying that when you're on an extreme point, dep corresponds to essentially the set of elements that you're dependent with. And here's another picture in 3 dimensions. So one thing actually I should mention, like, let's just look at this polytope for a minute. You can always, in some sense, sort of group elements together and look at the polytope associated with the grouping. I mean, one way you can sort of imagine it is by sort of looking at this two-dimensional polytope. It's kind of hard to imagine. But that would be like, for example, defining a new, you can always group together the ground element. Like, what if I take V, take the element V is the ground set, and I define it as V1 union V2, which is a partition, right? And I can define some new function, F bar, which is equal to 2 to the 1 comma 2 to R, such that F of A is equal to F of the union of I in A of V of I. Right? In this particular case, it would be a two-element guy. So this is like a little simple two-element polymatroid defined by partitioning of the original ground set. And it's still submodular based on the properties of submodularity. This is something that also we looked at in lecture 2. So what we're doing here, if this isn't clear why we're calling this A and B, essentially what we're doing is doing exactly that. We're sort of treating A and B as two grouped elements, subsets of the ground element, and then treating it as a projection, the polymatroidal projection of A and B onto two dimensions. But two dimensions, one dimension according to the subset A, one dimension corresponding to the subset B. In this particular picture that we're looking at, when we're looking at here, you can see that if the current element here is X, right? There's X. Now we want to move in the positive E direction, right? So the positive E direction is what way? Is this direction. Now we can't do that, right? But if we move in the negative A direction, which is there, we can move along this skeletal edge and stay within the polytope. So this basically means, therefore, that dep X and E contains A. Right? Now, does dep X A contain E? So this is saying if we want to move in the positive A direction, can we move in the negative E direction and do so? No. So therefore, this geometrically says that they're not symmetric in this sense. I mean, they're not like, just because you are in the depth of somebody doesn't mean that somebody is in the depth of you. Okay. And that's essentially what I just drew. So A is in the depth of E, but E is not in the depth of A.
It's only for this case, right? It's not in general.
It's only relative to a particular X. And in this particular X, we're talking about this particular submodular function, this particular point on the polytope. So we're only talking about this X right here. Right. I mean, as soon as we change X, everything changes. Right. But you can think about optimization strategies. I mean, the whole idea of polyhedral combinatorics, and the reason why we like polytopes and polyhedra to describe combinatorial problems is because we can then move around. We can actually do continuous style optimizations inside of like polytopes and get a solution. So you can think about X moving around inside of some polytope based on some rules in order to solve a combinatorial problem. And that's what we're doing here. That's what we're building up the tools to do. And at the same time gaining deep intuition, I think, in terms of what submodularity is. So therefore, it seems reasonable to say that, well, this dep function is equal to all elements A such that there exists an alpha such that if you want to move in the E direction, you need to move negatively in the X direction. And then basically, it's saying for E and SAT, because we really care about these saturated elements here. Okay. Okay, let's show this more formally tonight. Okay, so dep x of e, which is the 70s funk band function, n tight. Maybe it's an 80s funk band function, or 90s, I don't know. Isn't there a band called In Sync or something?
It's total 90s.
That's 90s? Okay, so I'm off by 2 decades. What's 20 years? I mean, in geological time, 20 years is nothing, right? So I mean, they're the same, right? Okay, so in sync, or sorry, in tight, basically we defined it as basically these are the elements that are necessary for tightness, right? And so the necessary for tightness, basically we got this from by taking the intersection of the E-containing tight sets, right? So going from get 13.41, we just see that, hopefully. Right? That's just the definition of what we mean by necessary for tight, and we use that from the lattice property. We get 13.41 from the lattice property. But then we can start saying, okay, well, that basically says that you're all E prime such that there exists an alpha greater than 0 such that for all A that doesn't contain E prime, but A that does contain E prime, this f of x, the f of A minus x of x is greater than or equal to alpha, and where alpha is strictly greater than 0. Okay, that means that you're not tight. So now what we're going to do is sort of unvectorize alpha. We go from alpha to 1 alpha times 1 EA, which works because we're assuming that E is in A, right? This makes sense. Now we're just rearranging things. We're just sort of putting x on one side. Actually, no, what we're doing here is we're realizing that this guy is equal to 0. And so we're just adding 0. Why is that? Because we're insisting upon A doesn't contain E. So when A does not contain E prime, so when A does not contain E prime as in here, this guy has to be 0. Right? Because that's the characteristic vector of E prime evaluated on A. We're summing only to the elements of A. E prime is not one of them, we get 0. Okay. Now we're rearranging. We're just sort of moving things around, and we're just moving x to one side. So we're just moving x over here. That's the only thing we're doing. Other than that, it's the same. Now here's a fun part. Basically, it's saying that what we're going to do is we're going to eliminate this stuff over there. So in this particular case, in 13.45, we've got this additional constraint, which basically says that E has to be in A, and E prime can't be in A. But what if it was the case that they were both in A, right? If they're both in A, like E and E prime is in A here, then we'd get that this vector is 0, and this addition would become vacuous. Doesn't matter, because we're choosing x inside of the polytope, right? And so that guy doesn't change the set E prime. Similarly, if neither of them are in A, so if we have this property, this guy's again 0, so this becomes vacuous still. So if they're both in A or neither in A, this guy becomes vacuous and it's clearly satisfied. Here what we're saying is that E is in A and E prime's not in A. The last one we have to worry about is what if E is not in A and E prime is in A. So the last one is, okay, so E prime is in A and E is not in A. But in such case, this quantity here, let's outline it in green, becomes just negative alpha. And since x is already in F, that means that x of A is less than or equal to f of A, so if we subtract off alpha, we're still in A. So all of the other possible things we could think about adding here, there's 4 possibilities, right? All of them are vacuous. So we don't need them. So we can just get rid of them. And so we just say for all A. Okay? This is still an expression for dep. But this now says, okay, well, we're doing this thing we're saying that this vector here has to be less than f of a for all of a. That's basically identical to saying this vector has to be a member of the polytope. That's the definition of the polytope. Right? So that's then therefore proving that basically this sort of exchange property definition of dep is identical to this minimal tight E-containing set definition, which is the minimal element of the sublattice. So therefore 13.7 and 13.47 and 13.48 are identical. Okay, so let's summarize the concepts that we've got. We've got this notion of a most violated inequality. We've got matroids by circuits, fundamental circuits. We've got minimizers of submodular functions form a lattice. We've got minimal and maximal elements of a lattice. Right? We talked about lattices a little bit. We've got the notion of x-tight sets and minimal x-tight and maximal x-tight sets, thanks to them being a lattice that exists. We have the sat function is basically a generalization of the closure. It's the polymatroidal generalization of closure. And it's exactly equal to the closure in the matroidal case. We've got the notion of saturation capacity, which can also be used to define sats. And we've got the notion of E-containing tight sets. And we've got the dep function, and how it's a generalization of the fundamental circuit of a matroid, and it's exactly equal to the fundamental circuit of a matroid when it's a matroid polytope. And here's a little bit more details. So the X-containing tight sets is equal to this. The polymatroidal closure is defined as equal to this, and we have these two different definitions. We've got the saturation capacity, and we have these two different definitions. By the way, we're going to use these definitions. In fact, there's a really nice proof of the min-norm submodular function minimization algorithm that uses these two definitions that we will do in this class. There's the saturation capacity defined there's the sat function defined by the saturation capacity. There's the notion of E-containing tight sets. This lattice of E-containing tight sets, and lastly, dep, or dry, or necessary for tightness, E-containing tightness. So the last two slides give us a summary of everything that we've talked about the last two lectures. Okay. What we haven't yet spoken about is the support of a vector. Okay. The support of a vector is defined as the non-zero elements. Now we hinted at maybe the support of a vector is somewhat akin to like an independent vector, right? Like if we've got a tight set, what is it that sort of captures everything about the tight set? If we've got an extremal point of a polytope, what is it that captures everything about the extremal-isness of it? So here's the definition of support. Actually, we're running out of time. Shoot. So let me just sort of give you a couple of examples. So obviously, the support of maybe I should skip this. Do you need an example of support? This is just the non-zero elements. You don't need this, right? I think everybody knows this. I think we should stop. I can't really, in good conscience, I can't go in good conscience proceed without diving deeper into your beautiful Wednesday afternoon when it's 80 degrees outside. So, are there any questions? Okay, so your homework should be graded very soon, I'm told, and there will be a new homework very soon as well on all of this stuff. So get a head start. Review the YouTube lectures, look at the slides, read Fujishiki's book, whatever you want to do to understand the stuff, because you will need to